going on, everybody? Welcome back, and I'm excited to be working on this some more. We got a lot, well, not a lot to do, but we have some important planning to do now for the next phase of the project. Hopefully, the internet doesn't have nearly as many issues this time as it did last time. I don't know what happened there, but it just completely died there for a few minutes. So, here's to hoping, and let's get started. We got to figure out how exactly we're going to connect everything up on the circuit board, because the Teensy only has so many connectors, or so many connections, so we got to make sure that we have enough for everything we're planning on doing. Let me look this up real quick. Teensy 4.1, that's what we're using. And then I'll pull up the work screen as well. So let me know how your Thursday's going. Just a reminder in case you're not here for the entire stream, but Tuesdays I will not be streaming next week, so just keep that in mind, and let's get to work. So, all right, so we have our Teensy 4.1 here, and we have all of these signal lines drawn. We have 5 volts and whatever, and that stuff's pretty self-explanatory, but we need to make sure that we know where all of our inputs and outputs are going, especially on things like this where you have the LCD screen and accelerometers and whatnot. We need to make sure we know where all that stuff is going. So yeah, that'll be a good time. All right, let's see here. So I pulled up the page here from the people who make the Teensy, and here it is. Nothing out of the ordinary. And then there should be a graphic here. Here's what I want. This thing right here. Because this details very exactly what everything is, as well as the extra parts that you can put on the board if you want to. I just want to double check. Make sure I'm not missing anything. That's interesting. I'll give some example projects here. Okay. Here's a really solid rundown of everything that's on the board. All the chips. So this is the full schematic. Oh, this is cool. All right. So I will do my best here, but basically we're just going to go through one thing at a time and say, okay, assign it here, assign it here, assign it here. And then hopefully at the end of it, we don't run into any situations where it's like, oh, we don't have enough of this or we don't have enough of that. Oh, we can download PDFs. Perfect. This is what I want. There we go. Excellent. So yeah, we just got to connect everything together. And I hate this numbering system. I mean, I get why they're doing it, but I hate the numbering system. All right, so best way to do this. I'm trying to decipher the power thing. Like, we got 5 volts coming in from the USB. We want that to go through the batteries and recharge them. But, well, it should still be able to supply the output, supposedly, if we limit it right. That's going to get tricky. Okay. SCL, SDA, SDA1, SCL1, SCL2, SDA2. Just quick overview of everything, trying to make sure we have the things I expect. Mosey, MISO, clock, Mosey 1. So this SDA, SDL stuff is the I2C Mosey, Miso, that's SPI. I don't know why this one's grayed out. And then we also need PWMs. Hopefully all that stuff is not too bad. 5 volts in, 3.3 volts out. Anything that we need to run on 3.3 volts, I think we can run from the Teensy itself. Like use it as our voltage regulator to run it, because we shouldn't be pulling more than this 250 milliamps. Anything 5 volts we should run from the voltage regulator. And I don't think we have anything other than that. All digital pins have interrupt capability. That's good to know as well. So our buttons and things will get connected there. Okay. Let's get started then. I need... Oh, let me turn the music back on. Otherwise, this is going to be a really slow night. If anyone has suggestions for other music too that I can get that won't cause my channel to be taken down, I am all ears. All right. We'll have to go through this pretty carefully. I wish there was a legend just to the coloring on this briefly explain it, but I guess it's not really necessary. Ooh, that's interesting. Okay, sorry. I'm getting lost in the weeds already, and I'm not even explaining what I'm doing. My bad. Here we go. This is what I want. The PCBA spreadsheet, but I want... Let's see. Pin, signal, and then device. This is going to take some time for me to figure out what exactly I'm trying to do here. All right, I think... All right, let's start with, let's see here. I guess we got to work our way around and do everything. So, and check it off as we go. And then we need to define what every pin will be connecting to. What if we just go around the board on the Teensy and list every single pin? I mean, that gets us in the right ballpark, right? Yo. I don't like how some of them aren't labeled. I'll do my best. So G being ground, obviously, because I wish they would number them all the way around. Instead, they've done G and then 0, 1, 2, 3, 4, 5, 6, 7, yada, yada. And then just in the middle, there's a 3V here. Continue the numbering, G, continue the numbering, 3V, G, 5V. And I totally get the point. Like, I understand why they did that. But I wish that that they hadn't. I wish they had just done numbers, just so I could write down a number for each one. Here's the back side of it. So what I was semi-interested in, what I was just looking at, was we got to figure out a way to connect the USB to the device. And so in order to do that, we have to connect to the USB pins, which I noticed are right here. I think. Oh, power. Interesting. Very interesting. They have it listed here too through these pins. I think this is perfect right here. This D minus D plus. This is what I was originally talking about when I was talking about bringing the data in. I needed a way to connect that. I thought I was going to have to splice some wires and then use a USB connector. But if I can connect through these through holes right here, these vias, that's perfect. All right, that looks solid. Off ground, 3.3 VBAT. Where is that on the board? Okay, right up here next to the USB stuff. That makes sense. That is a big capacitor. Just need to double check. So this thing that it's saying cut, where is that even at? Right here. It's up behind here somewhere. Cut to separate VN from UV USB if using external power. Do not apply more than 3.3 volts to any pin except VN and VUSB. VN being this one. So I don't know, what I don't fully understand is if, oh, this is a date time measurement. You can power the chip directly through this 3.3. That's kind of cool. Okay. The difference between what this +5 is and what this VUSB is. I'm guessing that this +5 goes straight to the VN. So I don't know, do I need to connect the 5 volts coming in through the USB to this and then cut it here because I'm using external power? I think that's what I need to do. Yeah, I think that makes sense. Okay. Something thereof. I'll need a way to denote these pins too because they're not labeled. See, this is like what I'm saying. I wish everything was just, every single one was numbered. It's like a very clear description of what goes where. Hopefully somebody made a model of this in Circuit Maker too. Otherwise, we're going to have to do it ourselves, and it's going to be a bit of a nightmare. Just to make sure we get everything in the right place for a footprint. All right, I'm going to list everything around the side, and then I'm going to have to go through and list these 5, this one, and this one in the middle. What's that one off? VUSB. Oh, I guess the power... Okay, so that makes sense, actually. Yeah, that is how you separate it, because the power that's coming in through this connector is going directly into this 5-volt pin. All right, cool. I'm sitting here saying all of this. I could probably just go look at the schematic that it was shown to figure out exactly what the heck is going on. Here we go. Oh, and this is beautiful too because there's measurements for all these vias. That's going to be such a huge help when laying out a footprint. Okay, so we have VUSB coming in through the USB, through that splitter or connector, whatever it happens to be, that we can splice. And I like that they left pads there so we can solder it back if we need to. And that's connected to VIN, which then goes through this regulator right here. Or no, FET. Do this. Oh, interesting. Is that tolerant? This is the regulator. That's the FET that it goes through. I guess there are some pins that are 5-volt tolerant on this device. That's kind of cool. All right, so regulator, and then that drops into the 3.3, which you can see goes around the board and powers any number of different things. Yep, through all these caps. Okay, that makes sense. So I need to, when I bring that voltage in through the USB port, I need to connect the voltage for VUSB here, but we're not going to use it for anything effectively. It's just another connection to have, and maybe good practice to have so that we can change that later if we need to, if we decide we need to. Okay. And then everything else will come in, the actual power will come through the regulator through the power pack on VN, which will then power the Teensy. Makes sense, and that makes sense why it's only 5.5 volt tolerant, because this is a 3.3 voltage regulator. So you can't exceed whatever the USB standard is, which is 5.5 on these pins. All right, cool. I know this is not the most interesting thing ever, or maybe not making a whole lot of sense, but I find it fascinating, and I'm happy to answer any questions. All right, and this will give us some idea too of what pins are going where. Oh man, not already. All right, so I think I'm going to do just exactly that. I'm going to go around the board here, listing off everything I possibly can for connectors. And then from that, oops. All right, from that, we'll be able to decide exactly where everything's going. So, working our way around the board, G, and then 0, 1, 5, 6, 7, 8, 9, 10, 11, 12. This is 3V. And then we have 24 to 41. I just realized how weird the numbering was here. I mean, look at this. 0, 1 through 12, 3.3, and then 24 on, because actually it goes 0 through 12, 13 to 23, and then down here 24 to 32, 33 to 41. And I'm guessing that's because everything above this point right here is on the Teensy 4.0. So they kept that all the same with the same numbering and all that, and then just added this section. But I'm going to number it all the way around the board in order, so my numbering is going to look weird here. So, 241. All right, and then G for ground, and then 13 to 23. If I get time later, I'll go through and color code this too. All right. And 3V. Yep. G. And then V, or 5V. Okay. And then we need to have our, I guess our USB connector. Which is this thing right here. So +5, D minus, D plus, ground, ground. What's the other one? VUSB. It's 5. Where is that? Ground. I need it to tell me. Because I see the V in here, but I don't right there. But that one that says +5, that's so weird. Is that this? VHST? What is that? Is this a 5-volt regulator? TBD3 is. Let's see here. TPD 3S014. Oh, it's a current limit switch. And ESD protection for USB host ports. Interesting. So this is just ESD protection. So we do need to connect the 5 volts to that. Oh, but that'll connect it, I think, to this. So we maybe don't want to. Oh, man. All right, this is a little weird. So what exactly am I looking for here? Processor in from 5-volt source. USB transceiver. Voltage bus. D plus. Works minus ground. Okay. Here's the application. So it's showing this V bus, this out, as if it's going out to the bus or something. That's kind of weird. I think this has to do with, so ESD protection stuff is a little odd the way it connects to the power and ground rails. Like, it's done in a very specific way because when you're protecting against ESD electrostatic discharge, static electricity, when you shock it and that comes through that signal line is what's weak, right? It's what, if that voltage comes in, static electricity shock, I mean, that could be as high as 25,000 volts. And if you have that big surge come through, then this chip is supposed to kind of detect that and grab it. And it usually does that through some specific diodes and things in a certain formation, so that when the voltage goes above a certain level, it'll drop back down. I forget what they're called. It's the type of diode where it goes the one direction, as a diode does, and then if an opposite voltage is applied that's high enough, then it reverses. So basically, it won't let current go the other way unless it reaches a certain voltage threshold, much like a static discharge would. I forget what it's called exactly. If anyone knows the answer to that, let me know, because that's a good little bit of trivia. It's not Schottky, is it? See, now I gotta look this up. No, that's a type, right? Yeah, low turn on voltage. What is the... It's a... I forget what it's called. I don't know how to search for it. I'm just looking for diode that reverses or something like that. I'm not getting the thing that I want. How about ESD diode? Maybe this will tell me. Zener diode. That's the word I was looking for. A Zener diode. A Zener diode is a type of diode that only lets current go through one way unless the reverse voltage is high enough, reaches a threshold, then current can flow back the other way. Thank you for joining me for that little adventure. All right, let's look at this data sheet and see what how this part works. I need to understand the pin out because they have pin numbers listed right here. So I am going to probably, I don't know if it's okay for me to put this on screen, but I'm going to. 1, 2, 3, 4, 5, 6. 4 is the out, and that's the one we're looking at here, right? Yep, out. Okay, so what does that mean? Power switch output, connect to load. Is this a USB output for like communicating with something else? I just realized that. Yeah, it's going into different pins. I think. Where's the other one then? I might have this wrong, and that kind of sucks if I do. D minus, D plus. Yeah, nothing else is connecting to that. Okay. So I've misunderstood something here. All right, so for the sake of moving forward, I mean, we're still going to stop and work on this, but I'm going to go ahead and finish labeling this out just for now. Yeah, okay, that makes sense. It's a 5-volt output. Dang it. All right. Plus 5V, D minus, D plus, and then ground and ground. So the pin names, and then the other one. Okay, there are pads that are connected to the primary USB, I believe, but they're just that. They're just tiny little pads. I don't know how I feel about that. So right here, this is the D minus D plus that's connected to the true USB with the VUSB coming in. This is a USB output for using the Teensy as a USB host. Okay. That makes sense. It's just aggravating because it makes this a little harder. See, the problem is the D minus and D plus are these little pads here, and we can solder wires to those very easily. But this is something that, I mean, it's in a lightsaber, right? It's going to go through shock. It's going to be dropped. It's going to get hit. You know, it's, even though we're not totally designing it with that in mind, it's going to happen. And things on little pads like this, when shock happens or things move around, tend to get tore up. You can literally rip these little metal pads off the board and then have nothing to connect to. So, yeah. Yeah. All right. So how do we solve that? Unless I could connect to the USB through this and do some sort of crazy bootloader thing to program, because I want to be able to program this in the future without having to open up the device, and that means connecting to the USB on the outside. So I have to connect the data lines somehow. I don't know if anyone has any thoughts of a good way to mount that. So if I look back at my schematic here, it doesn't list the test points here, but they exist. Let's see here. Let's look at a USB-C pinout diagram. I like Wikipedia. All right, somewhere in here there's got to be a pinout, right? Yep, here we go. Receptacle and plug. Okay. We're interested in the receptacle part. TX plus, TX minus, RX plus, RX minus, TX2 plus, TX2 minus, RX1 plus, RX1 minus. Let's look here. A6, A7. And B6, B7. Position 2, negative. I'll have to figure out how to translate it, but it looks like our differential pair exists. So, okay, that part's good. Let's see. Okay. Sorry, just looking through everything here. So USB 3.0, which is what this connects through, has a D minus D plus for the USB differential 2.0 differential pair, plus the receiver transmitter pair to go a little faster. So the issue now is how to translate this exactly to USB-C. And I think it's pretty straightforward. The only one I don't understand is the D minus D plus, which of these two to use. Interesting. Bus power. Maybe it's just enough just to go off one of them. I wonder if like I can look up a USB to USB-C schematic. Oh, wait, interesting. Okay, so I'm looking at a thing here. Just put 3 months. Spells like exactly how to make this. Another USB-C to USB legacy cable for USB-A 2.0. The connection looks like this. So which ones go to ground, which ones go to that, and then we care about, and it says A6 and A7 go to the positive and negative pair. So we use the A side. This is exactly what that's saying. Use this top one, the D plus, D minus here, not these ones. Okay. I suppose it doesn't. Okay, well, if they turn the cable in upside down or whatever, they're the opposite way, but I don't think that matters as much. Okay, well, they got the spec here. I bet I can read that later and figure it out more exactly, but cool. On the right track. So we're getting an idea of how to do this. Now, the problem is, how do we connect that? D minus and D plus. So that we can't use these ones, which would be really great because they're solid connections. We got to use these ones, which are not good connections. But let's see. But if we could, so here's what I was getting back to originally. A USB micro cable, because you can see the connector right here, which plugs into the connector. So plugs into this connector right here, and you can see the underside view here. And then, so we've effectively made that connection. And then after the connector comes out, we cut that wire, splice it, and solder those wires into some vias that we have on our carrier board. I'm going to call the carrier board the thing that the Teensy sits on top of. That's going to be our, here, this blue thing, the custom PCBA. That'll be the carrier board, because it carries the Teensy and everything else. That'll work. It'd be a solid solution. It just takes up space, which is the downside. And space is kind of at a premium. The other option is that on the carrier board, we put some vias right here and here, like underneath this thing, and then we run some connector pins through, not headers, but maybe like you can get little like posts or little pins basically that go through that are spring loaded that press up against this. We could do that. I don't have as much faith in those. Those are space efficient, but they don't do well with impact. They break easy. So yeah. The first option is definitely more durable but bigger. The second one is a lot smaller but breaks more easily. How about we do both? It doesn't, even though the other one is bigger, less space efficient, that's because of the big connector. But the two vias on the carrier board, are not that big of a deal. They're going to take up a very minimal amount of space. We'll probably have it anyway. So we put 2 holes out here for the data connector. We put 2 holes here for the data. And then we run the voltage up through here like we're supposed to, and then connect the ground to the ground. And we decide later which one we want to use. We can experiment. We can try both and see which one holds up better. And regardless of what happens, if one breaks or the other has too big, we can switch without having to change the design. Yeah, that makes sense. We'll go with that. Okay. So I need this pin added to the layout. I'm going to add these just so I keep track of them, and these as well just so I keep track of them. So let's see here. Whoops. Keep everything straight. This is the kind of stuff that what it's like to be an engineer during a day job. You're just making tons of decisions like this. And you have to keep moving forward, making decisions. So if you're indecisive, maybe not great. Okay, so this next one, oh, that is interesting. Power management. Ground. EBAT. I think this 3.3 volts is an input. I'll have to check that, but I'm gonna plan on maybe inputting something there, depending on where it's connected. Oh, I might not have to, actually. Basically, I want this to go into like a sleep mode if I turn everything off. Okay, VBAT, and then so we got you know what? I've just decided I'm gonna insert a column here, and we're gonna label exactly what all this stuff is. Action. How do I merge cells? Format cells. Merge cells. Yes? Okay, cool. All right, so all of this, all the way down to here, is the main outline. Outline. Oh, I hate that. Where's the vertical spacing thing? Running kind of slow. Stream doing okay? Now I'm paranoid about this after the issues we had last time. Borders, alignment. Vertical alignment. Middle. Okay. Yeah, that's where I want it. All right, and then this section is USB host. And then what do they call this section? Different things. I'm going to call it power management. I missed something. Program. Oh, interesting. A program pin. Oh, that's for the program button. So you can put something on the outside. Ah, cool. All right, merge those. And then I'm going to call this power management. I'd be very curious what these pins do. There we go. All right, and then finally, and we'll call this last one USB device. There's only the one pin, which is VUSB. Oh, and then D- and D+. We have to actually include that. and middle alignment. Okay. And then I want to make all this text. I want numbers. Cancel. There's a way to make stuff text, right? Open office. Change cell view text. You click data, text calls. All right, didn't find the answer yet. Cell for it. I've just got to figure out the right thing to Google. Oh, I think I was just didn't read enough. Format cells, numbers, category. Here we go. Text. Okay. And then align everything that way. Thank you. All right. So we can go through and do a few of these because we know what they're going to be. So ground, 3v3, ground, 3v3, we should say 5 volts for that, ground for that. All right, host is nothing. I guess we should do an NA if it's not connected, or NC, no connect. I am still going to connect the grounds though. The reason we're doing this is because I plan on putting pins underneath the board for all of this stuff anyway. So SB 5V, SB D minus, or DN. Is that what it is? D negative? I think so. Yep. And this is DP. I might include another column later here for like pin names. All right, so what I first want to do before getting all into this is figure out what exactly all this is, because I don't actually understand that. And I think I can figure that out from our schematic here. I care about these pins right here. One of those being the program pin, one being 3v3 program. Is that what that is? What is this chip? It's not the main processor. No. Yeah, not the main. And the on-off. That just goes into a thing on the board that's called on-off. I wonder if that's where I should put the power button. All right, we're looking up more stuff. If that's where I should put the power button, that's awesome. Pin's description. Alright, these are the pins on the back of the board. Those 5 pins are the same, except they're in a different position. Starting at pin 38. On-off pin. If you connected to ground for something like 5 seconds, the Teensy 4.1 will turn itself off. It will turn itself back on the next time you connect it to a ground for about a second or so. Interesting. Okay. Cool, but I don't know if that's exactly what I need. Well, maybe it is if we turn off the 3.3 voltage. Oh, yeah, because there's an enable on this, right? Isn't there? Yeah, there's an enable line. On requirements. So we don't... Okay, so the 3.3 turns on. So we could use that. This might work really well for our power button. Because it's a way to guarantee that like a code break or something doesn't stop it. And we could really cut the power like as much as possible. But the board does need to stay powered, right? For this to work. Pin to ground for the program pin. Alternate way to put the Teensy to programming mode. Depressing the button. If you connect it to ground for exactly 15 seconds until a red LED in the front blinks, the bootloader will reload a blink program of the Teensy that the Teensy shipped with, so you can more easily reload the Teensy if something went wrong. Okay. So that's effectively the reset button. I never thought about having a reset on it. Ground pin, 3.3 volt pin, VBAT. If you connect the VBAT pin to the plus side of the 3 and connect a ground to the ground side, it will use the coin battery to keep the time in a real-time clock. You can set the board starts up. Okay. My question is, if we disable this regulator, do we suddenly disable completely the Teensy? I guess we do, which means that this wouldn't work anymore, right? VBus. Basically, I love the idea of connecting our power button there. But if we do, then we hold it down for 5 seconds. It shuts down the 3.3 volt regulator. And as far as I could tell, that would kill the chip, right? But what's the point in shutting down the regulator otherwise? How does that work? I have no idea. Okay. Okay. I'm just reading a forum over here to see exactly how this goes. Weird. Oh, SparkFun has a thing on it. I'll pull this up here so that you all can see this tiny text that I can't read. Here we go. Authorize a power shutoff feature by connecting a push button to the on-off pin. The 3.3 volt power It's disabled by holding the button for 5 seconds and turning back on by a brief button press. I'm assuming this means exactly what it says, that you can basically just you can shut off that thing and turn off the board. I just don't know how it turns back on. It doesn't make sense to me. Let me look at this chip again. Maybe there's something I'm not seeing here. Don't know if y'all can hear that somebody's revving their engine outside. The enable is active high on this particular chip, on this voltage regulator, I think. The LDO and shutdown mode. Okay. Honestly, I should try this and see what happens. Because that's a really cool feature that would make this a little easier to do if I get it working right, but excuse me. The only reason I'm not going in just like saying let's do this is because I just don't understand exactly how it just doesn't seem like it should work. Like I'm missing something very important here. Namely, how is the Teensy powered if the regulator is turned off? Because it's effectively going to kill everything. Well, I don't know if anyone else has the answer. It's a really neat feature if it works. I was just looking on all these other forums I find on off pin. Let's see. Basically, everyone's just saying, hey, it works. Okay. I'm thinking what I might do is I'm going to connect to this on-off pin, but I'm also going to connect to some other pin as well, just to be sure. One of the things I'm worried about is that I think the only way this could work is if the VBAT was connected to a battery. And I really don't want to do that, so if that's the case, we're in kind of a rough spot. Although I guess we do have a big battery on the board that we could use if necessary, but that means adding another regulator. Okay. Let's go for both. All right, so program ground. This one is going to go to ground. VBAT, I think for now, well, actually, I don't know. Do we put a spot and a connector there just in case? Maybe not a bad idea. Yeah, I think we do just in case. All right, and this 3.3, I believe, is a 3.3 out, so... Let me check the schematic again. Oh, there's going to be a lot of this. Where's that header? Oh, it's just listed. Yep, 3.3 volt. Yep, that's on the output of that. So, okay, so that's just a 3.3 out. Okay. So this goes to 3v3. VBAT is maybe connected. We'll label a signal 3v3 in. Whoops. Program pin. Do we have a reset button on this device? I don't think so, because this erases it. It's useful if it gets bricked, but if you hold it, but we can just hold it down anyway if we open up the case, because it has a button on the board for it, I believe. Yep. If we look here, program, there's a little button right here, and we can see that button right there. So no point in, I don't think, putting like a little reset like pin. What I was thinking of, one of those little pinholes that you have to like stick a pen in to push down, because if you do that, then it's just going to erase the device, and then the user's going to be out of luck. So not connected. Okay, on off. I believe this is our power button input. I'm just realizing the way that we got to do this and label everything. Nah, we'll figure it out. I don't want to make this too complicated. All right, so this is our power button. So let's go look at our drawing here. What did we pick again? Adafruit 3350. I remember that being a fun little thing. Rugged metal push button. This is the 16 millimeter. This one. I wish I could have one of these so I could feel it. See if it is easy to press and everything. Oh man, I forgot about all the PWM stuff on that. Alright, cool. Alright, so we said power button in, goes to the on off. And then I believe we're also going to, and we said that we'll put device pin device. Does this thing have like a named pins? If so, that would be awesome. But I don't think it does. Red, blue, green, C+. How many wires are on this thing? I just realized that driving this is going to be kind of a nightmare too. We might have to do some sort of like PFET thing or something, because we're going to have to drive current to this device. Yeah, these chrome plated metal push buttons are rugged, but certainly not lacking flare. Up to 1/4 inch thick, and you can fit these in place. There's even a rubber gasket to keep water out of the enclosure. That's kind of cool. On the front of the button is a flat metal actuator. On the back, there are 2 gold contacts for the button and 4 for the RGB LED, 1 anode and 3 cathodes for each red, green, and blue. Power the anode at 3.6 volts and light up the red, green, and blue LEDs by pulling their designated contacts to ground as you desire. There's a built-in resistor. Oh, well, that's convenient. And if you want to use this with a higher voltage, say 12 or 24 volts, simply add a 1K ohm in series with the LED cathodes to keep the LED current at around 20 milliamps. You can PWM the RGB pins to make any color you like. So there will have to be, we can put NFETs because they're on the negative side. On the, it's the cathodes, right? Yeah. So the anode can be powered at 3 to 6 volts. I think we go with 5, right? And really make these things bright. And then, okay, that makes sense. Sorry, I'm talking to myself. So the other side of it's connected to ground, which is what we want. PWB in. And it doesn't really have a name. So, I don't know. Button 0. And button 1 goes to ground, I guess. And then we want to put this, oh, and this is, we want the Adafruit 3350. It's going to be exciting if we have to change things. All right, we want this on a digital pin as well, just in case we have an issue. So we got to pick one of our many pins here. Preferably not something with anything like already on it, like the I2C or the SDA, because we're going to be, or SPI, because we're going to be communicating with those. Anything else, though, honestly, could work. So I guess we go with, let's just go work our way around the board then. How about pin 2? So pin 2, we'll get the same treatment. There we go. To be in. And then we'll probably need to double check. Oh, we probably don't need to have a disconnect on that. I think we'll be okay. Okay. So that's unintentionally the push button done. I probably should have made a list of everything we had to do. Power button. Or it's not done actually because we have to do the 3 PWMs. All right, well that one was a little easier then. So you notice that a ton of these pins have PWMs on them. So I think we just do the next 3. 3, 4, 5. So red, RGB, green, and blue, PWM. Okay. I'll just say button red, button green, blue. And then you know what? I'm going to add an extra column in here. Or actually, I'm going to do one after. Notes. Just for anything that we need to remember. I'm going to say use NFET for N-type MOSFET. All right. Connect button 1 to ground. And then merge these. And format the alignment to the middle. Okay. Actually, I think I could do that with just everything here. There we go. Excellent. All right. So that's push button done. Next is LCD screen, which I never bothered to verify the communication type. I really hope it's not SPI. Really hoping for an I2C win here. All right, let's pull up New Haven. Oh, they have example code. That's kind of cool. Look at these guys being awesome and useful. Is this the device I picked? I think so. Weird color, though. Picked blue. Maybe I should have picked white. Show me a data sheet. Specifications. Here we go. Liquid crystal display module. Side white LED backlight. Negative blue. Oh, interesting. Okay. I'm going to have to go through and relook at this. Also, oh, I remember why we picked this, because it had these pins. But it's still weird. It's tiny, though. So it has potential. All right, well, it gives us everything to connect to here. CL, size, serial data, serial clock. I think that's I2C. But I don't know that it would send it. No, SPI. It is SPI. It just doesn't use the return line. Ah, that's another SPI. Although I guess we can share one with the accelerometers, because we're not going to be using this display while we're using the device. I don't think. Although it'd be really cool too. Oh, but that would be that hard to do stuff real quick. Okay. Yeah, we can make this work. So this might actually make our simplify our circuit some. Voltage 3 volts VDD, 6 volts VLCD. Oh, I remember not understanding that. The whole 6 volts thing. I wish we could change the color of it. But getting something that would do that is pretty expensive. Okay. Oh, excuse me. Supply, power supply, power supply. Okay, I got a ton of stuff that's got to be connected. VDD, VSS. What is that 6 volt thing? It only shows up here. 6 volts VLCD. There's a lot going on here. There's 3 volts. How much current does it take? Supply current, typical, 1 milliamp, max. Oh, okay. Well, that works. Supply for LCD, contrast, VLCD, 6 volts required. I don't know if this works for us. Anode, cathode. Supply voltage for LCD and logic, 3 volts. That 6 volts doesn't show up anywhere. It shows up in 2 places, but never on a pin. How on earth does this work? Any thoughts, anyone? Pins 1 through 17. Is there any other pins shown? Hold on, down here, 1 through 17 is listed, and then A and K. Where's A and K? Because we're going to need those as well. I'm looking for it. Oh, these big posts. I'm just now seeing it. All right, so they should give a layout here. Is it these square ones? This one and this one? Are those supposed to be like pads or something? A and K. Okay, I think I'm looking at it. It looks like they are metal posts. That's kind of weird how they do that, but it makes sense, I guess. Interesting. Curious how to pull that off. But yeah, that's exactly what they are. Huh. Okay, interesting. So, just real quick. I had to zoom way in on this web pages, which is why it looks weird, but yeah, you can see them right here. It looks like there's just a metal contact on one side of it, honestly. But that might just be the picture looking weird. Okay. All right. Well, that's a good start. So that lets us know what we need to connect to. Man, fitting this board in here is going to be wild. To make sure nothing collides. Okay. Let's see those. Pretty straightforward. What is A0? Register select. A0 instruction, A0 data. That's a direct connect. Interesting. Okay. Active low reset signal. Active low chip select signal. Right. So there's a chip select because it's an SPI. Totally got it. There's so much going on here already. I love every bit of it. All right, so it looks like we're going to be using the green. Chip select, Mosey, miso. Miso 1, S clock 1. Chip select, S clock. Where's the other miso one? There it is. Okay. On pin 1. Oh, but we haven't used that yet. Chip select 1. Chip select. So I'm guessing. Okay, so the chip selects are on standard GPIO, so we could always just not use them as the chip select or whatever. So I'm going to put one of the accelerometers on SPI 1, which would be Mosey 1, S clock 1, miso 1, chip select 1. And then I'm put the screen and the other accelerometer on the unnamed SPI. Mosey miso, S clock, which is where? Here. Why is that also the LED? It's going to blink as communication happens for no reason. All right. I guess I had to put the LED somewhere. So we'll do that and then pick 2 of the chip selects and put it on that. Oh, excuse me. And then I think that, yeah, it does it. Okay. And then we got to come up with the lines for the other things. Man, we are going to burn through IO. This is going to be awesome. So for the screen, I'm going to need a really long line here for the part number. So we said that, so the screen's going to go on the standard SPI. So 10, 11, and 12. 10 being the chip select. Screen. CS. And then that's Mosey, miso, and S clock is on 13, all the way down here. SPI clock, okay. Wow, it's amazing me how little progress we made tonight because it takes so much time to think through all this stuff. Okay. So master out slave in is where the data is going. So that's line 13. No, or pin 13 on the device. Master out slave in. So 13. I really need to format that to text. Device is the ridiculously named unformatted text. NHTC1, whatever. Miso is actually unused in this particular instance, so we can just say that's a no connect. All right, chip select line. CS1, active low chip select 17. Oh, I guess we don't do that. We're going to merge them. Oh, I put that in the wrong place. Anyway. Okay. All right. Clock goes to SCL, which is 14. Oh, I didn't mean that. Pay special. I don't want to paste the format. There we go. Close enough. Okay. So that's the clock, and then we already have the chip select and the Mosey. I think that's all. Oh, we need to come up with a signal for the register select. And then looking at our thing here, I guess we just pick the next GPIO that we haven't used already. So we could do this one. Green A0. And that is going to go where? $15. Oops. Okay. And that's to the screen. Man, it's gonna be really scary buying this board, and like, because I don't think I can breadboard very much of this at all. So it's gonna be a little terrifying buying the board to test out if things are working properly, and just building it, hoping for the best, hoping it doesn't explode. Oh, we need a reset as well. Yeah, I think I'm gonna do that. And then I think too, because we're going to want to be able to go in and out of programming mode, we're going to need a way to control the power to the backlight. Screen backlight, and that's going to have to be to a FET. Use pfet. And that's going to connect to, is it A? I think, yeah, that's the anode. Yep. A. And the screen reset connects to 16. Everything else is just internal. There are other connections, but they're not to the Teensy. So like the power supply and stuff. Man, this is gonna be really fun to figure out how exactly all this works. Oh, this is awesome. I love this specification document. It gives a breakdown of the command codes here that we have to send to it. Setting the page address or whatever. We get to write a whole library for this. Maybe they have one. That would be great. But we might get to write our own and do all that. There's going to be so much programming with this, and I cannot wait. I'm not even sure that I can be able to afford to do everything, so I'm kind of taking a risk here. Anyway. All right. Let me go ahead and define all this as text. Make it easy to understand, or at least align it. Numbers, text. Okay, and then align it this way. Thank you. All right, cool. Well, we've already used a ton of this I/O on this thing. This is going to be so much fun to try and route. Just to try and get all... This is going to be a complex circuit board, and I can't wait to see it. Okay. So what is that done then? I think that's the screen done. Now we need the 4 buttons that are going to be input that the user uses to help control what's on the screen. I guess we just keep working our way down the list of I/O. So we'll just label them TCT for tactile switch. It's W0. One, 2, and 3. I didn't think about there being multiple of a given item, so I wasn't ready for that. I'll have to figure out a way to notate that. Okay. Let me double check. Is that okay to put that there? No, it's not actually. 24 and 25 are fine. We need 26 and 27, so I'll have to move these down. All right, there we go. And then these will be connected to ground on the other side, so I'll have to use pull-ups with them and everything. It's all good. All right. Paste special unformatted text. Okay. Oh, that's the device pin. Yeah, we want to just take that and put that there. And then we'll notate it by doing this, because there's no underscores in any of the part numbers as far as I can tell. So, can be used to do that. Hey, that did work. Okay. And we'll just say button 0, I guess. Or switch 0. There's not really a good way to notate that. 3. Okay. Making good progress. Let's merge those. All right. So 9 is still not used, so we could use that for something. Or we could leave it alone. Either way. All right, so those are our buttons. Our speaker. Oh, we got to go to our amplifier. We got to control it from the amplifier. Yeah. I am totally not ready for this. I have no idea if I'm doing this speaker circuit right or not. I think I'm going to have to get somebody, unless somebody can tell me, I'm going to have to look up, or go talk to some people I know and see what they can tell me. Alright, ROM semiconductor, speaker amplifier. Let me see a data sheet. Cool. It looks like there's only one line that connects to... Let's see, yeah, VDD ground, NP, bias, SDB, and yeah. SDB is shut down. Where's the input? Positive differential input, negative differential input. Oh, so we gotta put it in the positive. Okay, so... so shut down. So this is a shutdown pin, and I need to understand exactly how that works. I don't think I need a controller from the Teensy. I think rather it needs to be, well, maybe not controlled from... Anybody want to hazard a guess? Okay, so when it's high, it's active. When it's low, it's in shutdown. We could probably, just so you all believe me, here it is. We might just be able to tie it to the 3v3 rail, because we know that when that powers up, that then we can turn the speaker on. I'm just worried about, like, if there's like, it'll be static, like noise or anything. Maybe we want to shut it down until we actually want to use it. SDB, SDB. .24 microamps at most, so hardly anything. Oh, that's the whole what the whole chip uses. Control pin, SDB, input voltage. High level is over 2 volts. Low level is 0.3 volts or lower. Just trying to see if there's anything else shown here that'll help me understand how this works. I know how it works, but... So I wonder if it's necessary to shut it down. From the Teensy. I guess it couldn't hurt. We could put a big pull down on it. That honestly seems like it makes the most sense. And then just run it to a pin on the Teensy. Yeah. I need to know what its input voltage is. 2 volts minimum. Okay. So that's what it's spec'd to. You have to get above 2 volts. Yeah, we can do that. Action release. Does this have to be connected to 5 volts? Operating supply voltage. 5 volts. It does. Okay, so it detects when that drops low. It shuts down. Interesting. So when you shut down the board at 25 microamps at most, probably more like 0.1 microamps. Okay. There's a lot going on here. Alright, so what would be next on this list? 28 and 29 already taken, so 30, 31, 32 on that side. So one of these has to be the input for the signal. NP. Yeah. Alright, let's do that. Let's do NP, and then let's do SDB. And then device pin 3, 1. Use external pull down. And then this is the amplifier that we picked. And paste special unformatted text. All right, there we go. All right, working our way through. I'm actually honestly kind of worried we're going to run out of pins. There's a lot to do here. But I think we've hit most of the big... Well, no, we haven't hit most of the big stuff. Jeez. All right, we're going to run the NeoPixels. I never thought to get a driver chip for the NeoPixels. I'm not sure if we even should now. I think those are controlled through SPI as well, which would make this even more of a nightmare. Because that makes that bus really busy. So yeah, I think we just direct drive them through some GPIO. Yeah, I think that makes sense. And then, what was I going to say? Oh, we have to use a level shifter. But we can use some FETs for that. Alright, so let's just knock out these. Let's do both the NeoPixel strips, and then I'm going to call it a night. And I think 30, 31, 32 is the last one on this side of the board. I think I'm just going to flip to the other side of the board. And just go to 34, 35, because those are standard GPIOs. So yeah, 34 and 35. And what should we say those are? Blade NeoPixel. And Hilt's NeoPixel. And we'll say use level shifter. And I think they call it DN on the device. I wonder if we should be able to turn the power on and off for these things. If we have the I/O, maybe I'll add that. All right. blade is Adafruit 138. And 4957. Those are going to be fun to work with. Okay, and then do we have the ability to turn them on and off? I think so. I just like having the ability to turn everything on and off on this board. Cycle power for everything. Just so, like, worst case scenario, if things start getting stuck or whatnot. I mean, we won't know it for sure, but we can just reset. We can do a hard reset on things. Yep. Blade power and hilt power. We'll just do them on these ones. And use EFET. And VCC, I think is what it's called. I'm just kind of guessing on that, but I can change them later. All right, this is literally like one entire side of the Teensy basically used up. Okay. Yep. That's what I need for now. All right. I apologize if the commentary wasn't that interesting tonight, but I'm just working through trying to figure all this out. So thank you all for joining me tonight. And reminder, I'm not streaming on Tuesday. I will again next Thursday. But this is fun. We're getting somewhere. And it's interesting to see it all coming together. We're now getting into like we've done the overview. We've decided the kind of parts, the general design, like block layout of the circuit. But now we're getting into the weeds, into the trenches of how exactly we're going to do this and deciding all the tiny little details. And it's just going to get even more in depth from here. So this will be cool stuff. All right. Y'all have a good night.